In this video, we're going to look at verifying a few identities using the half-angle identities, potentially also including the power-reducing identities, the double-angle identities, and the sum and difference identities. At this point, anytime that you're asked to verify an identity, you have to assume that every single identity that was previously taught and or learned can be used in these problems. So the first identity we're going to verify is that the tangent of theta equals to sine of 2 theta divided by 1 plus the cosine of 2 theta. You'll notice that if we look at our identity sheet, that is not an actual identity anywhere on this paper. So what we're going to have to do is come up with a set of potential steps that will help us get to the conclusion that these two sides of this equation are actually the same, or sides of this identity are actually the same. I'm generally always going to start by working with the more complicated side. So tangent of theta, I'm going to leave alone. There's not much I can do with it. The only thing I really can do with it is change it to be sine over cosine. So I might keep that in the back of my mind. I might change it on my paper. I might just leave it and not deal with it at all. I'm going to start with this side here. Another reason why I'm going to start with this side here is because I want all the interior angles of every single trig function to be the same. So with this theta and this 2 theta and this 2 theta, either I need to change this tangent so that it has a tangent of 2 theta or something of 2 theta, or I have to change these things here so that they no longer have 2 theta. And I think changing these things, because we have our double angle identities quite readily available, such as the sine of 2 theta, in this case, would be equal to 2 sine of theta, cosine of theta. And then I have 3 or 4 different options for the cosine of 2 theta, which I'm not sure yet which one is going to be the best option to pick. But let's go ahead and start converting things and see what we get. So on this side of the identity, I'm going to change the sine of 2 theta to be 2 sine of theta, cosine of theta, divided by 1 plus, and I'm going to have to select something for the cosine of 2 theta. Now, I could convert it to this one here, providing me with a couple of squared functions attached to that plus 1. That might help in the long run. I could potentially convert it to this one here, which means that I'm going to have all sine functions in the denominator. I'll notice that the 1 might add with this one here and give me 2 minus 2, which I can potentially factor the 2 out and manipulate that. And then here I can have the same thing, but in this case I'll have 2 cosine squared minus 1, and that plus 1 will still sit there. If that plus 1 still sits there, the negative 1 might cancel it out, and I'll be left with a single term in the denominator. This one might actually be the easiest one to work with for this particular example. I'm going to avoid that one simply to show that there's other ways that you can do this problem. I'm going to go ahead and look at just if I were to stick to the first identity and just use cosine squared minus sine squared and see what happens. So I'm going to have 1 plus, it's going to be one more time, cosine squared x minus sine squared x. That's what I'm going to first and foremost work with. With this particular setup, I'm looking at 3 different terms in the denominator, and that's going to give me kind of a headache. Again, I think that the last possible option for this example was going to work the most effectively. Just because it's going to work most effectively in this example does not mean it's going to work most effectively in all examples. It's just a matter of working with the identities enough to feel comfortable in picking which one you're going to be doing. Again, it means that you're going to have to work a few steps ahead in your mind, or at least write the steps on paper and say whether or not it's going to be good for you to keep going with that pattern, or maybe stop and start somewhere else. It's going to take practice, it's going to take work. I really need this denominator stuff to simplify down. So maybe I'm going to go ahead and just keep rewriting the top. What is one nice thing is that I no longer have double angles. I'm sorry, these are both thetas. I no longer have double angles in any of my problems, so I really just need to see this stuff on the bottom simplify down so that I can be left with just a tangent overall, or sine on top over cosine on bottom. With that, I'm going to go ahead and say, well, let's see here. I have 1 plus cosine squared minus sine squared. If I rearrange the order of this, I do have 1 minus sine squared theta plus cosine squared theta. And I know this stuff right here, based on the Pythagorean identity, remembering that that's not on my formula sheet, but it is a formula I can use at any given time. I know that sine squared plus cosine squared equals to 1. If I subtract the sine across, I get cosine squared equals to this. So I can then transform this problem into this. Now, the reason why I'm working with the denominator and not the numerator is because for two reasons. Number one, the denominator has those squared terms in them, and those squared terms are throwing us off in respect to the singular terms on top, and there's not much to do with the top, given that it's all in terms of sines and cosines already. There's a 2 multiplied out front, there's no half angles or double angles, and there's no powers. So there's not much that I can do based on any of these identities, especially considering the fact that all of the angles interior-wise are all the same. So focusing on the denominator where there's squared terms is probably the easiest way to handle this. And now you'll notice that if I were to simplify this, and hopefully you're thinking a couple steps ahead, if I add these two things together, I have 2 of those things now. The 2's can cancel out smoothly, and the cosine squared can cancel out with 1 cosine on top, leaving with a single sine over top of a single cosine, and that, sure enough, is the same thing as tangent of theta. So I have verified this using nothing other than double angle identities. And again, there's nothing wrong with that. I'm not sure exactly which identities they're going to ask me to use, but based on what they've provided is what's going to tell me what I'm going to want to use. Let's look at another example. Tangent of alpha over 2 equals the tangent of alpha divided by the secant of alpha plus 1. Now this one here might look a little bit more complicated to work with. But the steps are still, the steps that we're going to take are still seemingly straightforward. The first thing I'm going to note is that the tangent of alpha over 2 has a half angle identity in there. I'm also going to note that it's not one of the cases that are actually on my identity sheet, which is good, because otherwise I'd have to use previous identities to prove that identity, and I don't really want to have to do that unless I absolutely have to. Keep in mind, remember, if this identity they're asking you to prove is on the identity sheet, you can't just say, hey, it's proven, it's on the identity sheet. You have to use previous identities to prove that particular identity. So I'm going to go ahead and use one of those 2 options. But before I use one of those 2 options here on the identity sheet, I'm going to go ahead and manipulate the side that doesn't have any half angles. Now there's a reason why I'm going to start with this side instead of this side. Keep in mind that there are 2 different options for the tangent of x over 2, or in this case tangent of alpha over 2. There's the sine of x over 1 plus cosine, or there's 1 minus cosine of x over sine of x. I'm not sure which one is going to be most effective for me to use. Yes, I can just pick one and run with it, but I'm not sure which one's going to be most effective, and since everything's in terms of sines and cosines on my identity sheet for tangent of x over 2, why don't I convert everything in here to sines over cosines and see what falls out first. So on this side right here, I'm going to change everything to sines and cosines. Tangent is going to be sine of alpha over the cosine of alpha, divided by, my secant is 1 plus the cosine of alpha plus 1. In this case, I can go ahead and manipulate these fractions as much as possible to simplify as much as possible. I'll start by leaving the top alone, so sine of alpha divided by the cosine of alpha, all divided by. On the bottom, I'll go ahead and find a common denominator here, giving me 1 plus the cosine of alpha, all divided by the cosine of alpha. Now notice how I wrote these more slanted. I want the emphasis that this is the stuff on top and this is the stuff on bottom. And sure, there are fractions on top and on bottom. But notice how the denominators on top and bottom are the same. In this case, I can do that key flip change trick where the cosine on the bottom of the top will cancel out with the cosine of the bottom, in which case I'm left with the sine of alpha divided by 1 plus the cosine of alpha. With all of this simplification, again, notice how I didn't change the half angle side. I manipulated this side because my half angle side would have to convert to one of these 2 options. And sure enough, you'll notice it's actually the first option, sine of x over 1 plus the cosine of x. And this I can go ahead and make a mark and say that yes, this does verify because it is part of the identity sheet. And that's not what they asked me to prove. They asked me to prove that this was true, and they didn't limit what I could do here. So that's 2 of your identities being utilized, your double angle identities and your half angle identities. In the last one, we're going to go ahead and use that power reducing identity. So the last example we're going to look at is 1 minus the tangent squared of x equals to cosine of 2x divided by the cosine squared of x. This will probably be one of our more complicated examples as well, but it will take some work and we'll just have to think about what is most effective to be done here in order to simplify or manipulate this equation. The first thing I'm going to look at is the fact that I have a double angle, I have 2 different squared angles. So it might be most effective for me to just start with this double angle. Again, I might not need to use the power reducing or the half angle identities here at all, That might be the way that they want me to take, but I'm only going to use the identities that I think are most effective. Given that I have all these squared powers and one double power, or double angle, I'm going to work with the double angle first. I'm going to work with this cosine of 2x. The second thing I'm going to note is that I have 1 minus tangent squared of x. Well, tangent squared of x in my mind is sine over cosine. Sine over cosine tells me that I should really probably have a sine on top. So that, at least in this identity, eliminates me using this. I don't really want to use this because I want at least one sine function on top. I'm not sure which one's most effective in this particular situation, but I think this one's going to be the one I'm going to work with, also because I don't see a 2 on top here. And you'll notice that this sine function has a 2 inside. Please be cautious, and if you're not comfortable with doing some of this logic while looking at the identities, well then sure, pick an identity, try it, and just see what happens. It will build your skills on manipulating these trigonometric functions with the algebraic skills that you should be comfortable with in the trigonometric realm. So it's just a matter of practicing this material. And again, if you do it wrong, that's fine. The goal is take your time, work with it, and hopefully the algebra will work itself to get you to something that makes sense. The goal here is play with these identities, get them to be something that's going to make sense, and work with it. So again, in this particular case, I'm going to go ahead and work with our first identity. So this is equal to my cosine of 2x is the same thing as cosine squared x minus sine squared x. This is all still divided by the cosine 2x. And technically, here, I'm more or less done. Because I'm working 2 or 3 steps ahead in my head, I can see that I can distribute this division of cosine squared x. So I have cosine squared x divided by the cosine squared x minus sine squared x divided by this cosine squared x. And I know that this thing right here is 1 minus this thing right here is tangent. And sure enough, that is concluding this particular problem. Again, you probably could have used the power-reducing identities in some form or another, but I think they would have been more complicated for you and really not all that necessary to utilize. But that's 3 verifying identity problems. Again, if your angle's interior is different than all the other angles, I would start with that. If you can start with changing things to sines and cosines, that's also quite easy to deal with, especially if this side right here is just going to give you one step of manipulation. And then right here, again, change those interior angles to start, and then see what you can work with after that. If you can get all the angles in one problem to be all the same, then everything else kind of gets a little bit easier to work with.